the most beloved seabird on Earth hides a secret that shouldn't exist. In 2017, a dead puffin exposed a neon glow invisible to human eyes, a signal no one had ever seen. Researchers raced to prove it real, rigging UV lenses, shielding living birds, confirming the impossible. If these beaks truly burn with hidden light, what else in nature might be pulsing beneath our gaze? And could the fate of entire colonies hang in the balance? In February 2017, the harsh blue glow of a UV torch swept across a puffin carcass in a Nottingham lab. Jamie Dunning, a researcher used to cataloging seabird remains, watched as the dead bird's beak erupted in neon. The yellow ridges, the lamella and cirri, flared with a cyan green light, sharp and unnatural, like circuitry pulsing beneath the keratin. Dunning's lab notebook for that day reads almost like a confession. Impossible. The bill glows, not pigment, something else. Need confirmation. The specimen had died of natural causes. It was meant for anatomical study, nothing more. But under ultraviolet, the familiar orange and yellow plates of the beak transformed into something alien. The glow was confined to the ridges, not the whole bill, and it did not match any known pigment reaction. No sign of decomposition, no bacterial film, just a pure, deliberate fluorescence, as if the bird carried a message meant for eyes that could never see it. Dunning repeated the test, switching torches, swapping batteries, even moving to a different room. Each time, the result was the same. The beak's ridges burned with an unearthly glow, invisible in daylight, undeniable under UV. He checked older specimens, museum skins, anything with intact beak plates. The pattern held. Whatever caused the fluorescence was not an artifact, not a trick of decay. It was built into the living architecture of the puffin's face. The finding was too strange to ignore, but too fragile to trust without proof from the living. Dunning's mind raced through the possibilities: signal, accident, evolutionary joke. He knew that some birds, like parrots and certain auklets, had been shown to fluoresce under UV, but nothing in the literature hinted at this in Atlantic puffins. The ridge's glow suggested a purpose, a code, a signal flickering just beyond human perception. Yet every attempt to explain it fell short. Was it for mating, feeding, some unknown sense lost to human eyes? The lab's atmosphere shifted from routine to forensic. Each carcass became a potential witness. Dunning's colleagues, drawn by his astonishment, crowded around the next scan, watching as the beak lit up again. The question was no longer if the glow existed, but what it meant, and whether it could be found in the wild, among the living. The dead puffin's secret had cracked open a door. Now, the chase for answers had begun. 3 months after the first lab discovery, Jamie Dunning stood on the wind-scoured rocks of Petit Manan Island, Maine. The Atlantic roared in the distance. This was no controlled environment. Here, everything was alive, wary, and watching. The plan was simple on paper. Test living puffins, rule out every artifact, prove the glow was no trick of death or decay. But nothing about handling wild seabirds, even for minutes, is simple. A field kit waited in the grass, a Nikon camera, a filtered UV torch, and a set of foam and neoprene shields. Custom-built puffin sunglasses designed with Goldsmiths, University of London. The ethics were non-negotiable. No harm could come to the bird's eyes. The shields blocked every stray photon from reaching the retina. Every movement had to be quick, precise, and silent. Sam Ortiz, a field tech with a reputation for calm hands, readied the equipment. The team worked under the eye of U.S. Fish and Wildlife officers, every step logged, every minute counted. Dunning's hands slipped into the capture ring. A live puffin, banded for research, blinked in the morning haze. The sunglasses slid over its head, snug but gentle. The UV torch flicked on, and for a moment, nothing happened. Then, as the beam swept across the beak, the same cyan-green flare erupted along the lamella and cere, identical to the dead specimens. The Nikon's shutter clicked, capturing the glow in real time. Ortiz confirmed the reading. The third test, on a second bird, yielded the same result. 3 birds, 3 living witnesses. The glow was no artifact. It was woven into the biology of the living puffin, impossible to dismiss, impossible to fake. Each bird was released within minutes, unharmed, vanishing into the colony's chaos. The field log from that day, June 2018, reads, UV fluorescence confirmed in live subjects, no behavioral distress, glow restricted to beak ridges, sunglasses effective. The data was airtight. The phenomenon crossed the Atlantic, leaping from dead tissue in a British lab to living, breathing birds on a Maine island. The implications were immediate. Whatever the glow meant, it was real, persistent, and reproducible in nature. The field team gathered in the dusk, reviewing images on the camera's screen. There was no room left for doubt. The glow was not a quirk of preservation, not a chemical anomaly, not a product of human error. It was a signal, one that living puffins carried, unseen by any human eye. The next question pressed in from the dark. What purpose did this hidden light serve? The answers would not come easily. Maya Patel, a sensory biologist from Swansea, pulled up the first spectral scan on her laptop. The image looked like a heat map of a city at night. 2 luminous bands, one along the lamella, one at the cere, burning with energy at the edge of human vision. She traced the fluorescence with a stylus, marking the precise emission zones. The glow wasn't random. It hugged the beak's ridges, following the same lines that sharpen and fade with the seasons. In early spring, as breeding begins, the keratin plates thicken and the colors intensify. Under UV, the transformation is surgical. The neon signal emerges only when the colony's hormones surge and the old beak plates are shed for new. By late summer, as the colonies break apart, the plates dull, the glow recedes, and the face returns to gray anonymity. Patel explained the biology with a kind of forensic detachment. Puffin beaks are layered structures, she said. Keratin sheets growing in plates, each one replaced every year. The lamella and cere, those yellow ridges, are loaded with molecules that absorb ultraviolet light and spit it back as cyan green. The mechanism isn't pigment, but something deeper in the structure, possibly pterins or a modified keratin, though no one has isolated the compound. The fluorescence doesn't blanket the beak. It's confined to the ridges, as if the bird's face is wired for a private broadcast. Puffin eyes, Patel noted, are built for more than daylight. 4 types of retinal cones, including one tuned to around 370 nanometers, grant them a window into the ultraviolet world. What humans see as a block of orange and yellow, a puffin might see as a coded beacon, pulsing with information about age, breeding status, or health. The timing is too precise to be coincidence. The beak's hidden glow peaks in the weeks when mates are chosen and territories claimed. In the chaos of the colony, where thousands of birds jostle for ground, the ridges burn like a password, visible only to those who know how to look. Puffins are built for deception and display, but beneath the surface, their beaks reveal a different kind of power, one measured not in color, but in function. The same ridges that flare with ultraviolet light are part of a hunting arsenal honed for efficiency. Each plate, each groove serves a purpose. The interior of the beak is lined with backward-facing spines, like the teeth of a zipper, running along the upper palate. When a puffin dives, these spines pin wriggling fish against the roof, freeing the tongue to snatch another catch. The record stands at 60 sand eels, held crosswise, heads and tails protruding in a neat bundle. No other seabird can match that feat. This is not brute force. It is mechanical precision. The beak closes in a scissor motion, locking fish in place without crushing them. The tongue, thick and muscular, acts as a conveyor, pressing each new arrival into the row, never letting one slip. In the chaos of a feeding frenzy, a single puffin can dive, surface, and return to its burrow with more than a dozen fish, all perfectly aligned. The structure of the palate is a blueprint for honest signaling. No weak or sick bird could maintain such coordination. The ridges that glow under ultraviolet are the same ones that must withstand the pressure of dozens of fish, the salt and grit of the open sea. Every trip to the colony is a test. Only the strongest, healthiest birds return with full beaks. In the eyes of a rival or a mate, a beak heavy with fish and burning with invisible light says more than any call or display. It is proof, written in flesh and bone, that this puffin is fit to survive. Patel's voice, low and measured, cuts through the data. The beak is both a weapon and a billboard. Every adaptation, every groove, every plate serves two masters: survival and communication. That is what makes the signal honest. There is no way to fake it. Patel's fingers tap out a rhythm on the table as she pulls up a slow-motion video of a puffin launching from the edge of a basalt cliff. The wings blur, just a flicker at first, then a staccato pulse, 400 beats a minute. In the span of a heartbeat, the bird is airborne, slicing through the salt haze at 55 miles per hour. The body, compact and dense, is built for speed, but the real secret lies in the wings, short, rigid, and shaped for both air and water. Every muscle fiber fires in synchrony, pushing the limits of what a seabird can do. The same wings that drive the bird through Atlantic gales fold seamlessly as the puffin hits the water. There's no hesitation. The descent is vertical, a controlled crash, and then the bird vanishes beneath the surface, a black and white torpedo. Underwater, the wings don't stop. They beat with the same ferocity, propelling the puffin down to depths of 60 meters, deeper than most seabirds ever dare. The eyes, shielded by a nictitating membrane, scan the gloom for movement. Light fades, pressure builds, but the bird's lungs compress, bones absorb the shock, and the hunt begins. Patel narrates over the footage, her voice clipped, urgent. No other bird combines this kind of aerial velocity with submarine power. The physics are brutal. If a puffin's wings were any longer, it would stall in the water. Any shorter, and it couldn't lift from the rocks. Everything is a trade-off. Every beat is a calculation. The colony is chaos. But in the air and under the waves, the individual puffin is a machine, precision-tuned, nothing wasted. The hidden signals in the beak only matter because the body can back them up. A weak bird can't fake a high-speed dive. A slow flyer never returns with food. In the world of the puffin, every claim, every flash of color, every pulse of ultraviolet is tested against the wind and the sea. Only the strongest survive the gauntlet. Only the honest signals last. Institute records from the Gulf of Maine landed with a thud. Colony counts collapsing. Numbers that once seemed unshakable, now bleeding away year after year. In 2005, the cliffs of Petit Manan still pulsed with life. Thousands of pairs, their burrows packed tight, fish glinting in every beak. By 2022, the census told a different story. A 38% drop in breeding pairs. Entire sections of rock, once deafening with calls, had fallen silent. The data team at the Institute, led by marine ecologist Dr. Soren Lee, watched the trend lines bend lower with every spring survey. It wasn't just one island. Across the North Atlantic, from Iceland to the Shetlands, the pattern repeated, unraveling the future. Fewer chicks, fewer returns, fewer adults surviving the winter's gauntlet. The culprit hid in the water. Temperatures in the Gulf of Maine rose by more than 2 degrees Celsius over 2 decades. A shift as abrupt as it was relentless. Sand eels, the Puffins' staple prey, vanished from traditional hunting grounds, driven north or dying off in the heat. Each lost degree meant fewer fish runs, fewer meals for growing chicks. Lee's team logged the numbers. In 2012, an average burrow produced 0.8 fledglings. By 2021, that figure had halved. The connection was inescapable. The beaks that once flashed with color and under UV with secret light now returned empty more often than not. The Institute's database became a ledger of absence, banding records with no returns, burrows that stayed dark all season, hatch dates that never arrived. The risk was no longer theoretical. The colonies were thinning, the losses measurable in every scan, every count, every silent nest. The urgency pressed in, not as a warning, but as a fact. The Atlantic's clown-faced sentinels were disappearing, and the numbers left no room for denial. A midnight alert from the colony's acoustic sensors triggered a scramble. 12 tagged puffins, scattered across the outer ledges, began broadcasting a spectral pulse, an oscillation locked at exactly 0.8 hertz. The signal was invisible to the naked eye, but the field team's UV photometer caught the rhythm. Every ridge on every beak flickered in eerie synchrony, as if the birds were wired to a common clock. GPS logs, checked in real time, showed a sharp deviation, 45 kilometers off the expected foraging route. The detour cut directly across open water, bypassing the usual feeding stations. In the control tent, Maya Patel and Sam Ortiz tracked the anomaly, their screens pulsing in time with the colony's hidden code. The emergency protocol kicked in. Field responders, led by Dr. Soren Lee, moved to intercept, logging every movement, every beat. The team's radios lit up with terse instructions: monitor heart rates, check for environmental spikes, document any change in flock cohesion. No predator appeared. No storm swept the coast. Yet the pulse continued, steady, relentless, as if the birds themselves were broadcasting a distress beacon only their own could hear. Feeding stations, usually teeming at this hour, fell silent. The colony's energy coalesced around the pulsing 12, an invisible perimeter forming in the darkness. Every sensor in the network registered the same frequency, the same spectral shape, as if the ridge glow itself had become a language, one that humans could only watch, never translate. The night air pressed in, thick with the sense of a message passed through circuits not meant for us. Today, the true glow of the puffin's beak remains invisible to us, but not to them. As climate shifts and fish stocks vanish, these signals may flicker out before we ever understand their meaning. What we can't see still shapes survival. In a world full of hidden messages, what else are we missing? Let me know what you think below.